This webcast talks about some problems that involve linear momentum and the impulse momentum theorem. Okay, so first we're going to start off by just calculating the amount of linear momentum of different objects. Okay, remember that momentum is like mass in motion, and so momentum is calculated as the product of something's mass and its velocity. So that's usually written as the momentum P equals the mass times the velocity. Momentum is a vector, and so it does matter what the sign of the velocity is. So first here we have a German Shepherd. It has a mass of 40 kilograms, and it is running in the positive direction at a speed of 13 meters per second. That means that its velocity is a positive 13 meters per second. And so when we multiply this, we see that the German Shepherd has a momentum of 520 kilogram meters per second. And kilogram meters per second is the appropriate unit of measure for momentum. Okay, let's look at this child. Child has a mass of 23 kilograms and slides downhill. That's in the negative direction. So in this case, the mass is 23 kilograms. The velocity is in the negative direction. So it's a negative 21 meters per second. And so this child has a negative momentum of negative 483 kilogram meters per second. In the next problem about the bumblebee, remember that we would have to convert the bumblebee's mass, which is given in milligrams. We would have to convert that to kilograms before we calculate the bumblebee's momentum. And so just be careful with that to work in the standard units. Okay, let's do some problems with the impulse momentum theorem. So this theorem tells us that an impulse, which is represented by J, which equals the average net force multiplied by the elapsed time that that force is applied to the object, that force times time, or momentum, causes a change, or impulse, that impulse, which is the force times elapsed time, causes a change in the momentum, and that change in the momentum would be the mass of the object times the change in the velocity. Okay, so here we have a 60-gram tennis ball, so we need to convert this to kilograms, and so that would be 0.06 kilograms. Okay, that tennis ball is traveling toward the tennis racket at 23 meters per second. After the racket hits the ball with a contact time of 0.5 milliseconds, the ball leaves traveling at 49 meters per second in the opposite direction. Okay, and so here I'm going to say that the initial velocity is here's the person with the racket. The ball is initially moving to the left, so I'm going to say that the initial velocity is negative 23 meters per second, and the final velocity is 49 meters per second in the opposite direction, which is the positive direction. Okay, so it gives me the elapsed time, but I'm trying to solve for the average force. So I'm going to just leave that as F average times half of a millisecond. I need to convert that as well, right? Half of a millisecond is half of a millisecond, 0.0005 seconds. Okay. The mass of the tennis ball is 0.06 kilograms. The final velocity is 49. The initial velocity is -23. So I take final minus initial velocity there, and I can now solve for the average force. And it would be 8,640 newtons. Okay, let's look at this one about a car stopped at a traffic signal. When the light turns green, the car accelerates, and its speed increases from rest, or 0 meters per second, to 5.2 meters per second in 0.832 seconds. So again, I'm using that impulse momentum theorem, which tells me that the impulse is going to equal the change in the momentum. And so in this case, I do not know the average force, and so I can't calculate it as F delta t, but I can calculate the impulse by looking at how the momentum of the car changes. And that's going to be the mass of the car times the change in the velocity, which is final minus initial velocity. Okay, and so the passenger has a 70 kilogram mass. Their final velocity is 5.2 meters per second. Their initial velocity is 0. And so the change in the passenger's momentum is 364 kilogram meters per second. And that must also be the amount of the impulse applied to the passenger. Then it asks me, what is the average force that that passenger experiences? Well, the impulse equals the average force times the elapsed time. Since I know the impulse, I can find the average force by taking the impulse divided by the elapsed time. It's going to be the 364 kilogram meters per second divided by 0.832 seconds, and I get a force of 437.5 newtons. In the next problem, it gives us a graph that it says is the force that's applied to a 10 kilogram object, and it's asking us for the change in the object's velocity. So in this case, they're giving us a graph, and the impulse equals the shaded area, which is the area between the force versus time graph and the x-axis. Okay, so since this graph is approximately triangular, I can calculate that area. The impulse equals the triangular area, which is 1/2 times the base times the height. The base looks like it is 7 seconds wide, and the height is about 5 newtons. And so that gives me 1/2 of 35, or 17.5 Newton seconds. That's the amount of the impulse. That impulse should equal the change in the momentum, which equals the mass times the change in the velocity. So the change in the velocity, which was the question, right? Yes, what is the change in the velocity? of the object, it should equal the impulse divided by the mass, or the 17.5 Newton seconds divided by, it gave me a mass of 10 kilograms. And so that would leave 1.75 meters per second. Okay. I'm going to stop this webcast now, and we'll continue in a second webcast.